Hello everyone. In the last video we have discussed about the chirality and its importance in our everyday life. This is a chapter we are dealing with the stereochemistry. Now what do you mean by stereochemistry? The study of the properties of molecule with respect to three-dimensional space. Now what is the exactly meaning of this statement is? If you look at these two structures, these are derivatives of benzaldehyde. If you can see, this is a plain benzaldehyde, and here I have methoxy group at the ortho position of the benzaldehyde. Now, if I'm doing the reaction, if I'm taking these two reactant and I'm doing a separate reaction, let us say it is undergoing a nucleophilic substitution reaction. So when the reaction will occur, these two compounds will have a different reactivity. The reason behind this is the presence of these functional groups which are there at the ortho position. Now, these two are going to give us the different effect, and these are called as electronic effect. You can talk in terms of the resonance, you can talk in terms of the inductive effect. So here, the difference in the reactivity of these two molecule is because of the electronic effects are different because of we have the two different substituents. So this reactivity or this property difference is because of the electronic difference. But look at this. If you know this structure, this is a cyclohexane in the chair conformation. This is also the aldehyde group which is present. Now you can see in both the structure, aldehyde is present in the equatorial position. I have methoxy group besides or the neighboring carbon of the aldehyde group. This methoxy group have two different positions. Either it can be at the axial position or it can be at the equatorial position. Now, if I compare these two molecules, they have the same functional group. But now, these two molecules will show the difference in the reactivity is because of the presence of this methoxy group at the axial position or at the equatorial position. So here, there is no electronic difference. Rather, there is a difference in the structure or arrangement of atoms or the group in three-dimensional space. You can see here in this structure is more crowded compared to the axial position. That's why these two structures are going to show you different reactivity. So stereochemistry deals with such kind of reaction where the difference in reactivity is because of the three-dimensional space, not the electronic effect. I hope with these two examples, it is clear for you what is the difference between a normal chemical reaction and when I'm talking about the stereochemical aspect of the chemical reaction. Now, having understood the importance of the chirality in the last lecture, the next question comes in the mind is how to identify the chirality. Because we have seen the example of the thalidomide, which is a very important example to demonstrate if you fail to identify the chirality, it can be the hazardous in the field of the medicinal chemistry. And that's why the most important question, how we identify the chirality. Now, if you look at these two molecules, whatever the stereochemistry you have studied in your previous year, it is known for you that the presence of the chiral center. Now, what do you mean by the chiral center? It is a symmetric carbon atom, the carbon atom attached to the four different atoms or the groups. So, the one compound which is having the asymmetric carbon atom, we call that molecule as a chiral molecule. So now if you can see the first and the second structure, you can easily distinguish. The second molecule is chiral in nature, not the first, because the first is having two valencies are being satisfied by the same atoms, that it's the hydrogen. Even if I'll see the next, that is toluene, if you look at this structure, there is no asymmetric carbon atom. But if I'll see its derivative, I can see there is a carbon atom attached to the four different atoms of the group. We can say this is asymmetric or the chiral in nature. But if I'll give you few more example, for example like tartaric acid, Everyone knows these two first structures are showing us the optically active tartaric acid, and the last one is presenting the mesotartaric acid. So, if we can see the criteria that we have decided for the molecule to be chiral, that the presence of the asymmetric carbon atom. Now, this is satisfied here. It is containing the asymmetric carbon atom, and that's why we are saying this is optically active molecule. But look at this mesotartaric acid. If I see this, it is also containing the chiral carbon atom. In fact, there are two chiral carbon atoms present here. But still, we call this molecule as optically inactive. So this is one of the example where the molecule contains the chiral carbon atom, but it is optically inactive. All must be aware of this structure. This is called as a binol. And if you remember in your part 1, you have studied the RNS binol and how to assign the configuration also. That also you have studied. So everyone knows the binol is optically active. But if you'll analyze this structure, is there any chiral carbon atom present? No. So we can see this is one of the example where chiral carbon atom is absent, but still the molecule is optically active. And the tartaric acid, that mesotartaric acid, is the example where the chiral carbon atom is present, but still the molecule is optically inactive. That means the presence of the chiral carbon atom is not the only criteria, or that is not a sufficient criteria to say the molecule is chiral or not. Then what is the next part? That is how to identify the chirality. The simplest task is to perform the symmetry operation. If you want to prove that molecule is asymmetric, then prove that molecule is not symmetric. And that's why we need the symmetry elements. This is a chart I'll be sharing with you later on about the symmetry elements. So let us talk about it. So what are the symmetry elements? Symmetry elements are the different point of references, or these are the simple operations that we carry out on the molecule to find out whether it is having any kind of symmetry or not. Now, what are these operations? That may be a rotation, that may be a reflection, a center, or the you can say combination of rotation reflection that we call it as alternative axis of symmetry. So these are the different symmetry operations we perform on the molecule in order to understand whether the molecule is symmetric or not. So you have studied all these symmetric operations in your previous part 1, but let me revise all this symmetry operation one more time. So the first symmetry operation everyone knows, that is axis of symmetry, which is denoted by symbol Cn. If the molecule is rotated by the through the angle 360 divided by n, and if after performing that operation the molecule is indistinguishable from the previous or the original one, then we say the molecule possesses the Cn axis of symmetry. This is a order n, which is generally decided by 360 divided by how much angle you have rotated the molecule. So here I have presented a molecule, water. Everyone knows, if you can see, the blue atom is presenting the oxygen and the red atoms are presenting the hydrogen. So if you imagine the axis which is passing through this oxygen atom, and if I rotate the molecule through the 180 degree, then this two red atoms will exchange their position and I will get the new molecule. I will say equivalent. This is not original. This is equivalent position. Now this molecule, that is equivalent molecule, it's similar to the original one. And that's why we say the molecule has been rotated 360 divided by 180, that is 2. And that's why it contains C2 axis of symmetry. To go in more detail, I'll explain you one more example. This is of benzene. So benzene, if I talk about it, we have all the carbon hydrogen, they lie in one plane. So this is a planar molecule. Now, if you look at this benzene, I can say I'm just rotating it in the 3D. So if you'll see this, if I'll rotate it, you can imagine this axis which is passing through the center of this molecule. And if I'll pass this axis through the center and if I'll rotate the molecule through this axis, I will have the six different equivalent positions. And that's why I will say benzene contains one C6 axis of rotation. Now, apart from the C6 axis of rotation, the benzene contains few more axes of rotation. For example, if I see, let us imagine this axis which is passing through two opposite carbon atoms. Now, if I'll rotate this molecule, if I'll rotate this benzene ring, let us say, through this axis, you can see after rotation, I will get the equivalent position. You can see still I'm getting the equivalent position to the previous one. So how much angle I have rotated? I have rotated this molecule by 180 degree. That means this molecule contains the C2 axis. Now this axis I have passed it through the opposite two carbon atoms. So like that we have these two opposite carbon atoms as well as these two opposite carbon atom. That's why how many C2 axis pass are possible for this? There are three C2 axes which are passing through two opposite carbon atoms. Now look at this example also. If I, you can see I have taken this axis now. Now it is not passing through the opposite carbon, rather it is passing through the opposite middle of the two opposite bonds. So now let us say I'm just taking this molecule and I'm rotating through this axis. So when I'll rotate this molecule through this axis, I will get the equivalent structure after rotating it through the 180 degree. That means this axis is again a C2 axis. So there are total how many C2 axes? There are six C2 axes. Out of six C2 axes, the three pass through the opposite carbon atoms and three passes through the opposite carbon-carbon bonds. Now, as per the rule, when the axis of rotation passes through the carbon atoms, it is considered as more important compared to the other. Now, to decide the principal axis, the rule says the order of the C has to be the more. Now, if I see here we have a C6 axis and here we have a C2 axis. So definitely C6 axis has a more order. That's why this is a principal axis. And these are the subsidiary. Now, out of the subsidiary one, these are more important. Or amongst the subsidiary, I can call these as principal because they are passing through the carbon atoms and these are passing through the bonds. Okay, so the axis of rotation is the symmetry operation that we perform. We rotate the molecule through the axis and then we see or we find out whether we are getting the equivalent structure or not. To get the principal axis, the order of the Cn, that is n order, has to be higher. Also, if the order is same, for example like this, if this is also C2, this is also C2, then which one is the principal? The one which is passing through the carbon atoms. The next symmetry operation is the plane of symmetry. The plane of symmetry is simply called as a reflection. It is a plane that we imagine. If I imagine that plane and if that plane is dividing the molecule into two equal parts, as if the two part they look like the mirror image of each other, then I can call that plane as the plane of symmetry. Let us take the same example of benzene. Now if I see this particular benzene ring, as I told you, it's a planar structure. All carbon and hydrogens are present in one plane. So these are all present in one plane. So if you imagine this red one, this is a plane containing the carbon and hydrogen. So all the atoms are in the one plane. So above and below, there is a symmetry. And that's why I can say this is plane of symmetry. Now, if you remember, for benzene, the principal axis was the one which was passing through the center. So this principal axis is perpendicular to this plane. Therefore, this is called as sigma h. The sigma h, that is horizontal, plane is always perpendicular to your principal axis. Now, apart from this sigma plane, we also have this plane. You can imagine this. It's dividing the molecule into two equal parts. But observe this. You're passing this plane through the two opposite carbon atoms. So like that, we have again three different planes. So I can call them as sigma V. The way we have passed them through the opposite carbon atom, we can also pass them through the opposite bonds. I can even call them as sigma V. But you can see this I have called it as sigma V and this I have called it as sigma D. Now how to distinguish between sigma V and sigma D? Just understand. Now here I have taken this example again. This is my sigma, okay, which is passing through the opposite carbon-carbon bond. Now if you remember in the previous part when we discussed about the axis of rotation, these are also C2, these are also C2. But what I told you, which one is principal amongst these C2? The first three. Why? Because they are passing through the carbon-carbon atoms. So now, if I'll come back here, this is sigma and these are two C2. Now these C2 axes are principal one or the more important one. Now you can imagine this sigma is dividing the angle between these two C2. Since it is dividing the angle between the two C2, I will call this sigma as sigma D. Okay, so remember sigma D is that plane which divides the angle between the two C2 axes. So here the angle is divided, that's why it's called as sigma D. And the other one I can call it as sigma V. So in sigma we have three types: sigma V, sigma H and sigma D. Sigma H is the one which is always perpendicular to the principal axis. Sigma D and sigma V, they are the plane containing the principal axis. They're parallel. Sigma D, always remember, they divide the angle between the two C2 axes. So this is your second symmetry elements. Now let us go for the next one. Next is the invergent center. It is the imaginary or point in the middle of the molecule which is in the center, and if I see around it, all the points around it are at the equal distance and connecting the points which are equivalent. Let us understand this with the help of example that will be better. Now see this example. This is a simple cyclobutane derivative. I have methyl groups, hydrogen and methyl group. This is a point I have taken this is the middle of the molecule. I have extrapolated this line to one side where I am coming across the methyl group, and other side I'm again coming across the methyl group. So I'm coming across to equivalent groups, and that's why I will say it is having center of invergent center or center of symmetry. Again on this side also we are coming across the similar type of atoms. But now just observe the other molecule. This is a center. I'm coming across to similar atom, but other side it is not there. That's why this molecule is not having center of symmetry. If you want the molecule to contain the center of symmetry, it should be it should be symmetrical with respect to all the atoms present, not with respect to only one side. It should be equivalent from all the side. Then only we can say the molecule contains the center of symmetry. And the last one, that is alternate axis of symmetry. Alternate axis of symmetry is generally denoted by the SN, which is a combination of rotation and reflection. So after you perform these two operations, if you get the molecule which is equivalent to the previous one, then I can say the molecule is containing the SN axis of symmetry. So let us understand with the example. Again, I have taken that is cyclobutane derivative. Now imagine the axis which is passing through the center of this cyclobutane, and I'm rotating this molecule through the C4 axis. Let us say this is C4 axis. If this is C4 axis, that means I'm supposed to rotate the molecule 360 divided by 4, that is by 90 degree. So when I'll rotate it by 90 degree, what will happen? This molecule will shift to the next position. That means the next position will have X on the top, H bottom. This will shift to the next position. That means now I'll have, at this carbon, I'll have hydrogen on the top and the X down. So like this, I have arranged all the atoms. After performing the rotation, the next operation we are supposed to perform the reflection. But always remember, the reflection plane has to be perpendicular to the rotation plane. So my reflection plane has to be like this. So when I'll put the reflection plane like this, what will happen? All the atoms will interchange their position. The atoms which are below, they will come on the top. So when I'll rotate this, after rotation, sorry, after reflection, I will get this structure. If you'll see this structure, it is equivalent to the previous one. And that's why I will say the molecule contain S4 axis of symmetry, because we have rotated it through the 90 degree. That's why it is containing S4 axis of symmetry. So this is alternate axis of symmetry. And the last one is easiest one, that is identity. We are not going to deal with this identity part more in the stereochemistry, because we say all the molecules, whether it is chiral or achiral, they always have the identity. That is something you rotate the molecule through the 360. Now, if you rotate the molecule to the 360, of course, you're going to get the original structure, and that is called as molecule possess the identity. So there are total 5 symmetry operations: axis of rotation, plane of symmetry, inversion center, alternate axis of symmetry, and identity. We'll not focus more on identity, but these remaining 4 are very important. So at the end, with the help of symmetry elements, how to identify whether the molecule is optically active or not. So the molecule, to be optically active or chiral in nature, 3 symmetry elements, that is plane of symmetry, center of symmetry, and alternate axis of symmetry, have to be absent. Now, axis of symmetry Cn, that may or may not be present. But if I'll talk about the Sn, if you remember, Sn is a combination of rotation and reflection. So in short, you can simply say the molecule should be devoid of only Sn, because it's a simply a combination of reflection and rotation. So Sn, if you simply say the molecule is devoid of Sn, that is also enough to say. Now, as I said, the 3 has to be absent, but the fourth one, it may or may not be present. So depending on that, we classify molecule into 2 types. When all symmetry operations are absent, these are absolutely, they are absent, but if the Cn is also absent, then the molecule is called as asymmetric. And if the molecule is devoid of only 3, but Cn is present, then I will call the molecule as dissymmetric. So remember that chiral center may or may not be present in optically active molecule. That means molecule is not necessary to be always asymmetric. It can also be dissymmetric. Second thing, all chiral molecules are dissymmetric. Remember, what is the difference between asymmetric and dissymmetric? That they are having the difference of Cn axis. But what is a common thing between them? They don't have these 3. That means I can even call the asymmetric as dissymmetric, but I cannot call dissymmetric as asymmetric. All dissymmetric molecules are chiral in nature. All asymmetric molecules are also chiral in nature. But all chiral molecules are not necessary to be asymmetric. They can always be dissymmetric also. So the for molecule to be chiral, there are 2 categories. Molecules can be either asymmetric or it can be dissymmetric. Okay, so that's it from the symmetry elements point of view. Now after this, you will be solving one assignment. Now for assignment purpose, I'll be providing you a link of this Google slide. You can see on this Google slide, once you click on this link, you will see on the first slide, there are some instructions given. You will first go to the slide which is having your roll number and name. On the respective slide, you will find a structure. Find out all the symmetry elements present in that molecule and you can write your answers. I've given you the deadlines for this. Just follow these deadlines and complete your assignment. You can see the next slides. I've written the roll number and your name over there. The structure is given. Find out all the symmetry operations. Write it over here. For your convenience, I have written the symbols because then you don't have to search for the symbols while writing your answer. So you can just copy it from here while writing your answer and you can paste it in your answer. So like this, you will find there are different slides available and containing your roll number and your name. So go to your respective slide, solve that molecule, find out the symmetry operations and write down your answer. Thank you.